Hello, my friend. Today, I'd like to talk about the importance of being E. Okay, of course I know the spelling, right? But here I just wanted to make the analogy with the very famous short play by the Oscar Wilde of importance of being earnest, and refer to that of a very, very important value of E in IB mathematics. Well, you know, what I can tell you here is the study of E is really the focus of the what is high school math, right? That's high school math with the calculus really has started of the foundation of the E. So let's get to it. So, you know, you get to see a important value like the E in many topics in IB mathematics, right? Typically for topic 1, when you do the compound interest, you see, you know, yearly, quarterly, monthly compound interest gives you a bigger interest, but if you divide this by infinite many times, would you give it infinite value? And the answer was no, right? Because it was bounded. And then in complex number, you see the Euler's identity, the famous one. And then for topic 2, we have, of course, dealing with the exponential function and logarithmic function. And then for topic 3, we see a very nice link with the hyperbolic cosine and sine with the complex. Okay? And topic 4, yes, the, you know, normal distribution, you know, its probability density function is given by as such. So, you know, you cannot deny the strong bond of this value in many topics. Actually, this is the backbone. He's the backbone of everything you learn in high school. For obviously topic 5's derivative of itself is becoming, the function itself is the only function we have. Okay. All right. So what I like to do is to talk about an interesting idea of the E. Okay. With nice visual, right? I prepare a very nice animation for you, so please enjoy. And then it's got, you know, something with the proving with the limit. I like to talk about why 1 plus 1 over n has to converge to E. And then the first principle, Euler's identity, central limit theorem with the topic 4, and then the proving irrationality, right? Using something called the auxiliary function. Without further ado, let's get started. So yeah, these are the potential IA topics for you also. So you know, enjoy. So yes, the definition of E. Many definitions here. We have, you know, Maclaurin Series definition, etc. But here is the definition. Here is the limit of this sequence. Okay. So why? Why is the that's wordplay in Korean? Why is this sequence converging to E? Is the basic question, the primary question that we want to have to. So here's the thing, you know. Before we talk about the proof of the convergence, I'd like to talk about what it means by the definition. For example, when you cross the street in the green light, what do? Do you cross or stop? Of course we cross, right? But can I ask you why you cross? Can I ask you prove that we have to cross at the green light? Or is that the definition or axiom by the social norm? And yes, it is a definition. Often the definition you don't have to define, you don't have to prove it. You see, that's the axiom. That's the ultimate tools of mathematics. That's the ultimate fallacy of mathematics, in fact, because you have to have something that is fixed as truth, you see. We cannot question that, and often that is sometimes like the fatal error in mathematics, people say in the logical, because someone has to define it, you see. Why line is 180 degrees? Well, because we define it, right? So same thing. So what I'm saying here is, I'm not talking about why this limit is E, because someone defined it, right? But what I like to do is, why does this converge is what I like to prove it, you see? That E can be T or pi, whatever, if the history changed and someone gave the name of that limit as E. Pi. It depends on the definition. But what I like to talk about is that the behavior of the sequence will actually converge. You know, there are many definitions of the sequence, and if you go to the college and start working with the real analysis, you talk about very, you know, fancy epsilon definition. But that's not the aim of today, right? For the convergence, I like to actually orient everything from what you have seen from the exam. So if I see a May 17 paper 3 calculus paper, in this one you have to work with some partial sum and its convergence, right? Well, partial sum is also a sequence, right? So series is a sequence. And then at the end of the question, what you had to show the following. You had to show the sequence was bounded below by 0, so it's lower bounded, you see. And if you look at the behavior of the sequence, look at this. Un plus 1, the next term is smaller than the present term, un. Does that mean increasing or decreasing? Voila, it means decreasing. So you had to show it is lower bounded and decreasing. And hence, you had to mention that the sequence is convergent. So those two are another main theorem they use for proving the convergence, you see. So if you want to prove converging sequence, what you can do is that it is bounded and monotonic. and monotonic means increasing, decreasing. And if you want to show an increasing sequence being convergent, you have to show that it's bounded above. And that's the definition we would like to use, the one from the 2017 May, okay, for proving this sequence of the limit. So let me quickly show you that by a very nice visual. So as you can see, this is a sequence that is increasing, but it seems like what? Upper bound, you see? And if this is a sequence that is also increasing, but not bounded, as you can see clearly that if it was bounded, then it's going to converge closer to something called the supremum. That's the least value of the upper bounds. And if you look at it, if it's not bounded, as you can see, it's gonna just go above the bounds and then diverges, right? So that's what we have. Okay, so then, this is the sequence we have, you see? And let's try to plug the values in. If you try to put the values of 2, 3, 4, 5, etc., the value becomes like this, you see? And if we show the behavior using the sequence, it is increasing, but I don't know if it's bounded, you see? And just because some first values increase, I cannot say it is increasing generally. So what you still have to prove analytically for this sequence is to show that it is, increasing and bounded. So those are the two major aims that we're going to do. So let's get to it. So for that, yes, we're going to use a typical technique from topic 1 called a binomial expansion. So I'm going to do the binomial expansion term of this. So if you expand the binomial, if I quickly remind you, my friend, sigma, so if I have a plus b to the power of n can be expressed as a sigma notation of the following, right? So binomial coefficient, a to the power of n minus k and b to the power of k. So that's the binomial expansion we have, isn't it? And then if I use the same thing where my a and b are 1 and 1 over n respectively, so I don't really have to care about the 1, right? That's what we have. But for this one, instead of writing as a sum, what I like to do is to simplify further, especially with the binomial coefficient. Remember, n choose k is what? It was a n factorial over n minus k factorial times k factorial, isn't it? Another way we also tend to write is the, reduced form. So it's going to be n minus 1 goes all the way down to n minus k plus 1. So we have k many terms above and then divide by the k factorial. So that's the typical one. And that's the form I'm going to use it on my series here. So I use the, binomial coefficient with the second one, the n minus 1, n minus 2 goes all the way down to n minus k plus 1 is what I had, right? So that's the binomial coefficient. But you see, I got the over k factorial. But now, look, I had the multiple of 1 over n to the power of k, where you divide this by n many times. So I can do n all the way down n here. So each k many terms will be divided by n, is what I've written it here. And I put the k factorial in the front just to distinguish. Okay? So far, this expansion is just typical, you see? So now, if you simplify further by doing the long division, that's gonna be 1. If you do the long division here, that's a 1 minus 1 over n. And obviously the second term would have been 1 minus 2 over n, etc., and it goes up to the k many terms, okay? From 0 terms to k many terms. So we got this. So that, my friend, is my sequence here. So my sequence is looking like that, you see? What I want you to realize is that each term here are positive. You see? This is a positive. That is a positive. This is also positive, you see? Because I'm multiplying by the factor that is a difference between 1 and then the 1 reciprocal of an integer. So as you can see, as you can realize, this ratio is going to be always smaller than 1. They are always smaller than 1, you see? And if you subtract from 1, it becomes positive. So you are now looking at a term, product of positive terms. And think about it. So if that's my un, if you go with the un plus 1, that means on top of un, you're adding all these product terms that are all positive, right? It might got really small, but still it's a positive, you see? So if you're adding a positive number with the positive number, would that get bigger or smaller? You're right. Oops, it gets bigger. It gets bigger. So un plus 1 is obviously bigger than the un because you're adding the positive term as you grow, as you proceed. So we can say that it is indeed increasing. Okay? Typical way to show the sigma with the positive term, adding it. No problem. Easy peasy, lemon squeezy. So we just prove the increasing. Okay? So that should do. Now let's move on to the boundedness. Okay, so let's have a look at whether it is a bounded above. So this is the binomial expansion we had, and then we expanded this one out, the binomial coefficient, try to do the long division with the n, but this time I'm going to do it differently. This time, indeed, I'm going to expand by the series. So this is what we have, right? This is what we have. And then up to the n many term, right? Easy peasy and lemon squeezy. So then let's have a look at the listed out value. Let me list it out more elegantly so that you can see it all at once. So it goes from the n equal to 0, 1, 2, 3, all the way up to the n many terms. Oh, that's great. But now what I'm going to show you is two inequalities. But here's the thing. Right now, I'm showing you this inequality like paper 3. If you're given such inequality, that would have been with the paper 3 style question. Okay, so first I'll give you the first inequality. It says 1 over k factorial is less than 1 over 2 to the power k minus 1. This indeed is true, right? You can prove this by induction. But you see, k factorial is obviously bigger than 2 to the power k minus 1 for k value bigger than or equal to 2 for the integer, because, you know, k factorial multiplies bigger than 2 as it gets more. But 2 to the power of k only multiplies 2, you see? So 2, 3, 4, 5, 6, 7, 8, 10 would be the 10 factorial, where it's going to be 2, 2, 2, 2, 2, where it's going to be 2 to the power of 10. So what I'm suggesting here is that this is obvious. Hence the reciprocal, which change the direction because of the positive value. But of course, you should be able to prove this by induction. Try yourself. And then the second one is also an obvious fact, right? Because if you look at the n to the power of k, you're multiplying k many terms n many times. Sorry, k many terms by n, right? n. But if you look at the numerator, I'm reducing it, you see, n by 1 each time I proceed. So n minus 1, n minus 2. So obviously, who's bigger? N to the power of k is obviously bigger. So if you divide that numerator by n to the power of k, which is bigger, the ratio is obviously going to be less than 1. Easy peasy, lemon squeezy. So that would have been the paper 3. Paper 3, out of no context, they'd have given you the inequality, ask you to prove it. Honestly, for both of them, if it's a paper 3, you should prove it by induction, even though it looks obvious. Okay, no problem. So that's what I have, okay? That is what I have. That's great. So the reason I brought that is the following. So remember, my sequence here was given as such. But now, using such inequality, I like to derive an upper bound, you see? So if I look at the upper bound here, my friend, look. So I got the 1, they are the same. No problem. But if you look at with n equal to 2, check this out. Check this out. So what you have done, my friend, is the following. That n choose 2 over n factorial is the same as what? Sorry, n choose 2 over n squared is the same as this inequality, right? That would have been n times n minus 1 n squared should be less than 1. We already proved it. So that would be just replaced by 1 here, okay? And if I got the 1 over 2 factorial, from this inequality, if you put 2 here, you get 1 over 2. So I replaced the 1 over 2 as an upper bound, you see? Now let's move on to the next one. I got the n times n minus 1 n minus 2 divided by n to the power of 3, which should be less than 1. So I put the 1 in here as an upper bound. Remember, this is an upper bound. You see, I proved that inequality before. And then, the 1 over 3 factorial will be replaced by 2 to the power of 3 minus 1, which will be 2 to the power of 2, which I have it right here. So the reason we are using this inequality is that your upper bound will actually be just made out of the geometric series. So now each term is going to be bounded by this sequence, which is a lot easier for me to compute the series because this geometric series with the common ratio half. Voila, that is great. That is wonderful. So if you proceed with using the geometric series, you see that it's going to be the an, my sequence, is bounded by 1 plus the geometric series. We can simplify as such. And if you set n to infinity, you see, he's going to be bounded by 3 because that's the, if you send n to infinity for this geometric series, it just converges to 0. Right? That is wonderful. That is wonderful. And for me, this is the paper 3 result. This is a paper 3 result. But for me, what I want to ask you is the following. If you wanted to write this one as an IA, and then the way you wrote here would probably not get you huge marks for your personal engagement. Because here's my critical question, critical feedback to you if you wrote this one as an IA. My question is, how do you know this? How do you know that you would have used this inequality? Of course, you can say, oh, textbook was telling me. Of course, I'm sure there are many documents describing this inequality, asking to use for proving the upper bound. But, why? That is the essence of a personal engagement. That is really something called investigation. You must know how we came up with this inequality. inequality. My personal advice, how you came up with this, you should start from here. You should start from here. You know this series, you want to find the boundedness, you see? So then I know I must have an upper bound. But of course, your upper bound could have been different series. You know, if you can find a better series, please go with it. But you see, I'm dealing with the series. I want to find the upper bound, which I would probably know the limit of, you see? And then the one that you know the limit well is probably something to do with the arithmetic series or geometric series. Well, arithmetic series does not have any convergence because, however, how tiny the common difference is, if you add infinitely many times, it's going to diverge. On the other hand, if you look at the geometric sequence, if the common ratio is between -1 and 1, you know it is going to converge. So I can control better than the present sequence that I absolutely have no clue about because it's a bunch of combination and square. That would have probably justified of coming up with such inequality. Well, obviously it has to be still analyzed correctly and thoroughly. But my advice here is, if you wrote it as an IA, you cannot claim that you have information for free. It's not taken for granted. You have to explore. Okay. But anyways, but now we go back to the paper 3 style. So yes, it is bounded. So that's beautiful because we just proved, my friend, that it was increasing using the positive term, adding it, and then showing that by comparing with the geometric sequence and series, that it was bounded above. Therefore, I can say that it converges. It's going to converge to a value between 2 and 3, because the least value was 2 and the upper value is 3. And hence, for that limit, whoever came up with first, Leonard Euler, call it E. Okay? Hence, we call it E. We are not proving why we call it E, but we are proving that the sequence does indeed converge. So that's important. That's very important. Another variation of the limit that you do here is, if you replace the x, it becomes e to the power of x. It's very, very straightforward to prove, because if you use, that one as a substitution, you can come up with the same thing. Right? Try to see yourself, if you were given this limit, if you can derive this. You can derive it. Okay? Try to see yourself. But another variation here is that the 1 plus u to the power 1 over u, as u goes to 0, is also E. Okay, so this is actually also a very important variation, because you often use it for the calculus when you're trying to prove for the first derivative of the exponential function using the first principle, and that's what we are about to do. Let's get to it. So let's have a look at the proof of the derivative of exponential. We cannot take things for granted. You have to be able to prove it. It's not going to be the imperative knowledge. This is going to be declarative knowledge. When you claim something, when you declare things, it follows with the demand of the proof. So we use the first principle, rise over run, on the exponential function. Then it becomes like that by using the property of exponent, where you see the common factor as e to the power of x. So let's just factorize it. Why not? So if I factorize it, it became like that. So that, as you can see, e to the power of x is independent of the h, which is the gap, right? And then I can isolate this sequence. And my first bet is I'll probably put h to 0. If you put h to 0, e to the power of 0 is 1. I get 0 over 0. I still get the indeterminate form. I don't like it. I do not like it. So what you want to do is to explore the limit here. So let's see how we can use the limit that we just proved using the boundedness and monotonic to use it. So we're gonna use this variation. We proved this, right? And then we said that if you make the u as a 1 over n, you can have this following limit. Oh, well, in this case, I'm gonna let the h as a 1 over n. Okay, let me quickly show you. So for the first principle, we had the rise over run, and then we came out with this, and then this limit has to become 1 to show that the derivative is equal to 1. But let's quickly show it. So now we know, okay, 1 plus 1 over n as n goes to infinity was what? It was to the power of n was e, you see? And if I let 1 over n as u, then limit u going to 0, 1 plus u to the power of 1 over u becomes e. No problem, that's great. Okay, so in this limit here, what I'm going to do is the following. Check this out. I'm going to let e to the power of h minus 1 as a u. Okay, that's good. So look, if h goes to 0, u also converges to 0, right? Because, h going to 0, e to the power of 0 becoming 1, 1 minus 1 becoming 0. No problem. So that sequence is going to be limit u goes to 0. It's the same thing, right? H going to 0, u go to 0. That's great. And then I have, what is it? U over. You see? Then I will make the h as a subject using the inverse function of exponential, which is the logarithmic function. So if you make the h subject, then h is going to be ln 1 plus u. Voila, very good. So I got the ln 1 plus u. That is a great, you see. And then that u can go to the denominator by reciprocating itself. So this will be u converging to 0, 1 over u ln 1 plus u, right? So then by using the property of a logarithm, then I can make the coefficient as the, what is it? The power. So limit h goes to 0, 1 over ln 1 plus u to the power 1 over u. And check this out. Now if I send, if I send u to 0, we know that one will converge to e. Thanks to the limit that we proved using the increasing in boundedness. So now that becomes 1 over ln e, which becomes 1. Therefore, this limit will converge to 1. But yes, there are many things we skip actually. Can we say while we are getting the limit of a function, can this limit goes inside, you see? I'm not getting the limit of 1 plus u to the power 1 over u. I'm doing the logarithmic function of 1 plus u to the power 1 over u, right? And yes, for this one it works because it's a continuous function. But you see all these detailed things you'll be learning in college once you start working with the real analysis. But that's not our job at the moment. Let's just accept it. Then we can use it for the continuous function. It would have been mentioned in the paper 3. But yes, as you can see now, it converges to 1. We can actually prove it. You see, that's the essence of it. That's the essence of mathematics. You need to know why it works so that we don't work like ChatGPT, right? Deductive thinking, declarative knowledge is essential of being human. Okay, so that's great. So now we see that, the derivative of the exponential function is simply just beautiful, beautiful results. So let's move on. So that's the first application. So now that's the second one, right? We prove the limit, and we prove it for the first principle. No problem. That's great. Now let's move on to the next fun idea with the exponential function. And for the topic 1, we often see this beautiful, beautiful superstar. What is it? The Euler's identity. We saw the cis form is going to be the same as the Euler's form, right? So let's have a look how we can show that. I prepare a very nice visual for you. If you put this Euler form on the Argand diagram, try to transform it to the 3D, it sort of becomes a spiral. It becomes a spiral, you see? And then if you now sort of rotate around, look at this, on the real axis for the vertical axis on the 2D, if you look above, you see a cosine form, right? Isn't that beautiful? This is really looking beautiful. Now, let me rotate again with the 3D, because now I want to transform for the imaginary axis. If you go for the imaginary axis, my friend, you see what? Yes, the sine function there. And yes, you can sort of tell that this is going to be helix, you see? Why? The Euler form in the 3D looks like helix. A very good IA topic for you. Okay? So yes, look at this. Look at this. It's intuitively showing you that the visual of the complex form using the cosine and sine. So it's very nice animation. Beautiful. Okay, let's get to it. So yes, I want to show then, what was our aim? We want to show that the e to the power I theta is indeed the cosine theta plus I sine theta, right? For that, you need a lot of preparation. So for proving the limit of the sequence, we use the binomial expansion. For this, we're going to use the Maclaurin series, which we also learned in the syllabus. I want you to realize I'm trying to go through this as much as I can with the stuff that we already learned. For the first one, we learned the binomial expansion. We learned the geometric series. For the derivative of exponential function, we learned first principle. Now we're going to talk about the Maclaurin series. But for those of you who haven't learned the Maclaurin series, let me quickly wrap it up for you. So yes, it is a power series, which is a series with the polynomials, infinite series of polynomial. And it's got very interesting observation because, when it was your first time to learn something about the series converging, it was a geometric series, wasn't it? So for the geometric series, according to certain condition, it converges to a number, you see? Same thing for the power series. According to some condition, the series, the infinite sum of this polynomial will converge to a function. In this case, this power series converges to a rational function, you see? But then what comes to your mind is, well, okay, what about the sine? What about the exponential? What about the logarithms? Does there exist such polynomial, sum of infinite polynomial series, which is called power series converging to those functions? Is the premise of the Maclaurin series. And let's talk about how we can do it. Okay, so, the essence here is for you to find those coefficients. If I claim my series has, let me quickly go back to the previous slide. Sure, if you have, a function, and I want to describe the power series, what is very important for you is to know their coefficient. So we're going to determine what the coefficient is going to look like. And finding the constant term is pretty straightforward if you just plug x equal to 0. Then I get the constant, no problem. If you want to get the A1, you want them to become an independent term. And for the polynomial to make the A1, which is the product, which is multiplied by the x, if you want to make him isolate, if you want to make him independent of the x, you often just differentiate. So if I find the first derivative, if it's differentiable, of course, and then I can put the x equal to 0, then you can find the A1. Easy peasy, lemon squeezy. And now you can do this inductively, right? So that means you can do, recursively. You will do this pattern, right? Now, from the pattern recognition, we now know for the coefficient of the x squared, which we call it A2, I will differentiate him twice. So if I differentiate twice, I get the following, where he's independent of the x. So now if you put x equal to 0, everything else will become 0, and now we can isolate this. Then if you want to find A2, you divide by the 2 or 2 factorial to find the second, the coefficient of the second term. Lovely things, lovely things. Now you can generalize it, right? You can claim, now what? For the nth term, I would differentiate by n many times, and then divide by the n factorial. So if I quickly show the third one, yes, as you can see, it becomes divided by the 3 factorial. So now let's try to generalize. If we generalize, it looks like the following. Continuing this way, we will get what? The following infinite series and becoming as such, right? The nth derivative, kth derivative at 0, but still make sure divided by the k factorial to find the coefficient of the x to the power of k. So that's generalized form. However, here's the thing. If you want to talk about the convergence, you cannot take things for granted. What I mean by take things for granted is the following. For infinite geometric series, for example, there was a condition. We have the convergence of the infinite geometric series if we know, if and only if the common ratio is bounded by 1 and -1, you see? And for the power series, for the Maclaurin series, to claim that this series will converge to that function, you have to show some condition also. The condition is that the remainder term has to converge to 0, okay? So, let me quickly show you an example with the exponential function. So for the exponential function, I like to, do the typical method of finding the Maclaurin series by differentiating this n many times and plug into the 0. But thankfully, the exponential function is the only function whose derivative becomes itself. So if you put 0, it becomes simply just a 1. I'm very happy. So I can come up with the polynomial with the following generalization of the polynomial terms. And I like to compare by the graph whether those polynomials will look very similar to the function. Let's have a look. Sure, so if you graph the exponential function and linear function, let's go with the quadratic with degree 5. On the graph, let's see how it appears. It looks like the following. This is my quadratic function. This is my degree 5, and this is my linear. As you can see, close to 0, they're all the same. However, it's getting away, as it gets away from the 0, some functions are getting away from the exponential, but some functions still attain the very, very accurate approximation with the, the exponential, but still will diverge eventually. That's why we need the infinite series, right? However, showing the graph doesn't prove the convergence. For proving the convergence of a Maclaurin series, which is not in the syllabus anymore, it used to be, you have to prove that the remainder term also converges to 0, which is known as the Lagrange error term. So now, if you think it converges, what you need to do is to come up with the partial sum of to n degree polynomial, and then the remainder term, which goes with the following form, right? It used to be in the syllabus, so we had to learn it. But this Lagrange error term, our job is to show whether it's going to converge to 0 or not. Okay? Let me quickly show you, because I was going to skip it, but this is a really nice term to talk about. I don't know why they skipped it, but if you're interested, you should also write your internal assessment about it, right? Showing convergence of other series by exploring with the Lagrange error term. But if I quickly show you the remainder term, whether it converges to 0 or not, especially for the exponential function, looks like the following. Okay? So let me show you. So I want to show that. To show this, we have to show the remainder term converges to 0. So now we had a Maclaurin series. Maclaurin theorem states that when we have the nth degree polynomial, we automatically have the remainder term, which is defined as the such. And this c value, okay, is a value that is defined from the center of the series, which is a 0, and then whatever the x value that you arbitrarily choose, you want to find the c such that this becomes maximum error, okay? You want to talk about the maximum error. You want to make this remainder term as big as possible by arbitrarily finding the c in the given value of the approximation. And what are you going to do? Even that maximum error you want to show as we add more terms on it, and so forth, will eventually become 0, is the essence of the proof of the remainder being 0. So you want to show, first find the maximum error, and then show even that maximum error converges to 0. So that is what you want to do, okay? So for that, remainder term, what we can come up with for the exponential function looks like the following. Without loss of generality, what we want to know here is to show this sequence converges to 0. The typical way of doing this is called the ratio test for the infinite series. Again, it used to be on the syllabus for the topic 9 for paper 3 in IB higher level, but it's now omitted. They don't talk about this anymore. But the proof really essentially focuses on the ratio test, and let me quickly show you. How to find this limit is the following. So yes, if you talk about this infinite series, right, if you can show that the ratio of this sequence converges to 0, then you can show that less than 1, my bad, not 0. If it converges to the limit that is less than 1, then you can show that this infinite series converges absolutely. Okay, and it's not in the syllabus anymore, but just to show the essence of a Maclaurin series, I give it to you. Okay, so ratio test of the sequence comes like this, and as you can see, whatever the x value, if you set n to infinity, it will goes to 0. It will converge to 0. Therefore, that the sequence converges to 0 because it's a convergence series. If the sequence converges, then sequence has to converge to 0. The converse is not true, and the counterexample is the harmonic series. And then the radius of convergence is going to be all real. For this, you don't have to know, but I just wanted to show you, right, that to talk about the Maclaurin series in your IA, you should mention the remainder. Okay, no problem. Fast forward. So we can say that the sequence, sure, the remainder term does come, so very good. And then, proving that, that sequence is very nice. Knowing this, you can prove many functions converge. In fact, this series is the backbone of proving the remainder term of all the terms, all the popular functions that you do. When you study Maclaurin series, please not only memorizing the general form, please remember the interval of convergence as well. That's very also important, okay? So that's great. Let's continue. Now, we would like to use the Maclaurin series for the Euler's identity, right? So we had the exponential function as the Maclaurin series, right? We now have a different definition. The first, we had a limit definition. Now we have infinite series definition. For this, what I like to do is to substitute with the I theta. I'm going to let x2 I theta, and then try to expand this out, right? I like to see the pattern. And of course, what bothers me is that we have this imaginary number, and I like to see what pattern I can recognize. And here, what you realize when you have I, the even power will make things a real number, and then the odd power will make things imaginary number. Let's see what we can do. Sure. So I put it into the power of k, and then you recognize for the I to the power of k, things will be real if it's even number, and things will be imaginary if it's odd. Okay, so let's take that into consideration. So I got the even power, still have the alternating term. I got the odd power, having the alternating term. But as you can recognize, right, now you see that is a typical Maclaurin series of cosine. Remember, the Maclaurin series of a cosine function is an even function. Since it's an even function, it's going to be giving you the even terms. So it's going to be, sigma n equal to 0 to infinity, -1 to the power of n, x to the power of 2n, theta to the power of 2n, over 2n factorial. And that's exactly what's happening here. They use index k, no problem. That's the only difference. So you can let that to be cosine. For the odd term, it's going to be sine, right? So if you cannot just isolate the I, right, it's the independent term of that, so it becomes as such. So that's a proof of it, you see. Now because, you see, you prove the limit, you can prove the derivative of exponential, and then you can use for the Maclaurin series, you see. You needed those two, because in order to talk about the Maclaurin series, you need to find the coefficient using the derivative. So if you don't know how to differentiate, you cannot find them. But now, because you found them, you can justify the Maclaurin series of exponential, also working with the remainder term. And now with this, you can make many substitution. Well, in fact, this is also has to be defined, you see. How would I know if this substitution will be preserved for the infinite series, even if I'm dealing with the complex number? Because remember, those radius conversions we define only for the real number. Does it really work with the imaginary number? It has to be defined, you see. But, for now, we're approaching with the paper 3, assuming a lot of things to be true. So that is the proving Euler's identity using the Maclaurin series. Then let's talk about what else, right? So now we saw the exponential function where in topic 1, topic 2, and topic 3. In topic 3, what have we seen? We've seen it with the, mixture with the exponential function and then cosine and sine. And you can extend that idea later on with the hyperbolic function, which also has been very popular for paper 3. But now if I move to topic 4, where it seems like that it's not going to have any relation, the exponential plays again a critical role with the statistics, especially with the distribution. So the typical distribution for all the SOHS students learn is the binomial distribution. And then the binomial distribution probability that distribution function looks like the following. If it's probability of x equal to x, means out of n, I choose x many success, so I have a p to the power of x. You have to take into consideration of the failure of n minus x many times. So that is the probability distribution function of the binomial distribution, right? But for this one, what I like to do is to also come up with the expected value. Expected value of the binomial distribution is known as NP, and the variance is NPQ, right? You shouldn't forget that. But now, you see, that is my expected value, right? And look, if I let the n rearrange to the left-hand side, you got the proportion as an approximation of the mean over n. Okay, that, my friend, is the proportion right now as an approximation. And what I like to do is plug that into the binomial distribution and see what we get. Sure, so now if I see this, I'm going to put it into the binomial distribution. Sure, so now we see that the p was substituted by the mu over n, thanks to the binomial expansion expected value formula, right? So then from here, what I like to do is to rearrange a bit more. You see, by using the property of exponent, I can do the n minus x just minus x times to the power of n. No problem, because a to the power of m times a to the power of n is a to the power of n plus n, right? That's what we have. That's great. Then if I use the binomial coefficient and choose x, I have n factorial over n minus x factorial times x factorial. So that is great. So that's what we have. And now, here's the thing, I like to play around a bit. So please bear with me. Now I put this in the common denominator. I got the n minus mu over n, right? Please don't forget this. I put that into the common denominator, making it the same thing. And I'm going to use the power rule. So let's see what I mean by I'm going to use a power rule on the next line. So here, what did we have? We had a n minus mu over n to the power of negative x. But now, using the distributive property of the power, I can put that in the power of the numerator and denominator as such. And for the negative power, it makes things reciprocate. So for that one, it can be changed as n to the power of x over n minus mu to the power of x. That's what we have, isn't it? So that can be done as n to the power of x over n minus mu to the power of x. And now you can see that one actually cancels out, right? So now I'm only left with n minus mu to the power of x in the denominator. So far, so good. Now I can do another power rule there. Let me quickly show you. So here, look, check this out. So that is preserved. And now I'm pairing n minus a factorial, n minus mu to the power of x with the n factorial. You see? So now the form is put like that in the common denominator. No problem. Easy peasy, lemon squeezy. Let's now move on to the next term. So far, so good. So now what we want to do is to show how these limits will converge as n goes to infinity. But for the second one, you can sort of notice that's the limit with the exponential form that we already proved. So we're going to use that. But for the first one, if you think about, okay, if I use the factorial as a recursive definition, we can do the n factorial over n minus x factorial. And if I divide by the n minus x factorial, you still have how many of the following terms? I can have n times n minus 1 going all the way up to n minus x minus 1, and then n minus x, n minus x plus 1, etc., etc. I'm giving you the recursive definition. But the reason we have done so is that you can lose this denominator, you see? Then you have how many terms left? You have x many terms left here. We are using just the binomial coefficient. You are using just combination notation. And now the reason we have done that is you can actually now pair all this by the n minus mu, because all the numerator have x many terms, you can divide by n minus mu respectively x many times. So that's what I have, right? That's very good. And now, if you look at the ratio of each term, which I can pair them one by now, right? Because they're all by x many and x many, so I can pair them by one by one. If you send n to infinity, if you follow the leading coefficient, they all converge to 1. You see? They all converge to 1. So that is great. That is an excellent. Sure. So we pair them x many terms by now, so if you send to infinity, each term will actually converge to 1. Because, that one, it will just become 0 each time I send the n to infinity. No problem. So then the product now becomes nicely just a 1. The product will therefore eventually just become 1. Let's take a look into it. Yes, it will just become 1. Infinite product of 1. So that is just converging to 1. No problem. Thanks to our binomial coefficient understanding and the way we can factorize and using the limit definition. That is great. Now let's have a look at the second one. What do we have? We had this, 1 minus mu over n to the power of x. But then we know from the first theorem that that is the limit of the exponential function, right? You can easily prove it. So now if you make the substitution, you realize that this is going to be e to the power of now what? On the location of x, I'm going to replace with the negative mu. So I got the exponential function with the power of negative mu, right? So that's great. So now, all this limit of that distribution happens to be the following. We managed to change that binomial distribution into the following form by using the expected value of the binomial distribution as such, and then making the substitution with the proportion as a mu over n. And then from this, we realize this limit, okay, will actually converge to 1. And this limit will actually converge to e to the power of negative mu, thanks to the limit that we defined at the very beginning. Therefore, what we can say is that this becomes this following function. So that is used to be in the syllabus for the all the syllabus for the IB, but now it's only taught in AI. Is the Poisson distribution. So now you can show the binomial distribution. If you have many samples, then it will become, what is it? The Poisson distribution. So that's another use of the exponential function and its limit for proving the convergence from the binomial to Poisson, right? I just wanted to show you the application of E happening in topic 4. Very nice. The binomial distribution will converge to Poisson. That's an excellent case. But we haven't proved that it's actually a good probability distribution function. You have to know that it follows the axiom of probability, that if you add all that, it's gonna become 1. And you can easily prove so. So, because, that means probability of x equal to, what is it? 0, probability of x equal to 1. If I have infinite series, if you start plugging with 1, what do you get? 0, what do you get? I get the e to the power of negative mu, plus, what is it? Mu 1 over 1 factorial, and, e to the power of negative mu. E to the power of negative mu, mu square over 2 factorial, goes on and on and on. So you can see that there's a common factor, right, as e to the power of negative mu. Then I have mu factorial. So mu to the power of 1 over 1 factorial, mu square, 2 factorial, mu cube, 3 factorial, goes on and on and on. And then you realize that this is going to be e to the power of negative mu, sigma, n equal to 0 to infinity, mu to the power of n over n factorial. But that is precisely the definition of what? Exponential function. So it becomes simply e to the power of mu. So now we have e to the power of negative mu, e to the power of mu becoming 1, making this as a good probability distribution function because it follows the axiom of probability. If you add all the cases, it converges to 1. Hence this good probability model, right? So that's great. But now, who's gonna be, jaded with just touch the binomial and Poisson distribution from the discrete random variable, but who's also superstar? Yes, you're right. Another superstar for the continuous random variable is what? The normal distribution. So right now, what we want to show is that Poisson distribution actually also converges to the normal distribution. So let's take a look at it. Let's take a look. So how do we show this convergence? It requires actually a lot more interesting concept. But you have seen it actually. Let me quickly show you why. I'm trying to, orient these problems based on the things you learn and the things you have seen from the exam. And the very nice problem, I think it was one of the end problem in the section B on a May 13th exam paper. So if you're interested in, taking a very hard problem with the statistic, please take a look into it. But then at the end of the question, what you had to find was an expected value using some sort of a differentiation. Okay, you had to find a series and then you differentiate it, and somewhat you come up with this expected value. All right, and that is in a sense called the generating function. We don't learn this in the syllabus anymore. It used to be taught in topic 7 back in the day, but not anymore. But there's a function called the probability generating function or moment generating function. This is more general because it goes with the discrete random variable and a continuous random variable, and it's given as the following. This is an expectation function where we put exponential function instead of putting the discrete random variable. And then for the discrete random variable, it's given as such. We use a sigma. For the continuous random variable, we use a integration, right? And then the reason we are dealing with this function, it's called a generating function. What it means, a generating function, is that it generates a suitable value that I want to find for statistics, often what you want to do is to find a meaningful statistical parameters, such as expected value or variance, you see. And for that, this moment generating function helps you to find expected value. So it's a made-up function. Generating function is not fixed. It depends on the situation. And for statistics, especially when you're trying to find expected value or variance, we define the generating function as such, so that if you plug it in with your distribution, if you differentiate once or twice, it helps you to find the expected value or variance. Again, it's a man-made up question, the equation, to help us to find things quickly. It varies a lot depending on the purpose of computation. Okay, but anyways, so we carry on. So now we have learned the discrete random variable is a moment generating function. So, and the reason we do is if you find the moment generating function, if you put the derivative using the chain rule, it becomes like that. And if you put t equal to 0, then this becomes 1. Hence, you just get the expected value. You see, this is a very neat way of finding the expected value. If you don't want to do, product of the discrete random variable and probability distribution function, put that as an infinite series and find the limit. That's difficult, you see. But instead, if you come up with just the moment generating function and try to use some result from the calculus, especially for the convergence of a series, things can be solved a lot more quickly. Sounds very complicated, but if you actually look, into one of the case, in the following case with the Poisson distribution, you will get it. Okay, so let me quickly show you. So if I have a Poisson distribution, then x is distributed by Poisson over lambda, and this goes for AI students. That the expected value is known as just lambda. It's one of the distributions that uses the expected value as the parameter. And therefore, for that, and then the probability distribution function was the probability of x equal to k was e to the power of negative lambda to the power of k over k factorial, which we also proved using the convergence of the binomial distribution, right? No problem. So now, if I use the expected value, remember the expected value definition was expected value of x. In fact, if I just put the function of x, it's just the, sum of the function, random variable, times probability distribution function. So that's what I'm doing. I already have my probability distribution function, known as e to the power of negative lambda times lambda to the power of n over n factorial. On top of that, I multiply my function here, which is e to the power of tn, right? According to the moment generating function for the Poisson. Moment generating function for the discrete random variable. But if you look at that, it's a series, and for me, it's always best if you can isolate the independent term. It's complicated to talk about everything else. So I would take out this e to the power of negative lambda to the outside, because it's independent of the index of a sigma. So now I can put everything together by the power of n. And as you can see, this infinite series suddenly reminds you of what? Something to the power of n and something over n factorial. It reminds me of the exponential functions in Maclaurin series. Remember, e to the power of x is a sigma, x to the power of n over n factorial, wasn't it? So now this x will be replaced by lambda times e to the power of t. Therefore, I can have e to the power of lambda et. Then, if you now use the property of exponent, you can combine them together. You can just find the difference and then find the common factor of lambda. So this will be e to the power of lambda, e to the power of t minus 1. And why do we bother with this moment generating function? It can show you, it can prove, it can find you the expected value as well as the variance if you use the derivative well, okay? So if you differentiate this once, you get that. If you put now t equal to 0, check this out. If you put t equal to 0, this is 1 minus 1 becomes a 0. So I got the exponent to the power of 0. So that becomes 1, you see? And e to the power of 0 is also 1. So I simply just get lambda. That's it, right? So that's the average. That's the expected value of the lambda. So that's the proof of it. And we often use this moment generating function to find the expected value. Okay, why have we done that? Because I want to use those moment generating functions for the normal distribution as well. Okay, for the normal distribution, let's see how we can use the moment generating function first, right? So the moment generating function was the expected value of e to the power of t z. Now the random variable is z. But now, because it's a continuous random variable, I'm going to use integral instead of a series. So now this is going to be improper integral from negative infinity to infinity of that function. So e to the power of tx, because I decided with the dummy variable x. And then the probability density function. Remember, the probability density function for the normal distribution, although you don't have to memorize, it's in every book. It's in every book. It's given as 1 over root 2 pi, negative infinity of e to the power of negative 1 over 2 x squared dx. That's the probability density function. Oh, sorry, without the integral. And then you integrate to find the area, which will represent the probability for the normal distribution. Okay, that's great. Now, what we want to do is to be able to integrate this. It looks very hideous. However, it's not that bad, because now we got this result. What's the result of this? Because it's a good probability density function. If you integrate this function from negative infinity to infinity, it should become what? You're right, it should become 1. So you know that this integral alone will be simply root 2 pi, which I have proven in one of my videos with the gamma function using the differentiation under integration sign. Sorry, yeah. So you can use this result. So let me quickly use that for you. So now what I like to do is to put them all together. So I had e to the power, what is it? Tx minus x squared over 2. But I've just done the completing the square for you. This is the completing the square. Sorry, I haven't done it yet, but I'm going to do the completing the square. So this is the completing the square of this quadratic form. Just check yourself if you can do it. The reason I've done that is the following. So that integral, look at this, will become e to the power of, what is it? Negative x minus t over 2, this is a perfect square, right? Times e to the power of t squared over 2 dx. But I want you to please remember, sorry, 1 over 2 pi. I want you to realize that e to the power of t squared over 2 is independent of the x. So I can take him outside. So that is great. So I have a 1 over root 2 pi e to the power of t squared over 2, right? And then I get the integral from negative infinity to infinity, e to the power of, what is it? Negative x minus t squared over 2 dx. Okay, yes, I know nothing about that integral, but I do know the probability density function of the standardized normal distribution. It was negative infinity to infinity, e to the power of negative 1 over 2, so negative, x squared, dx was root 2 pi. So that's what I had, wasn't it, right? So now I'm interested in on that one. And for me, I like to use the integration by substitution. So I'm going to let, look, u as a x minus t. Then you see du will be dx, isn't it? And look, if it's definite integration by substitution, you have to change the bounds as well, you see? But look, if you set x to infinity, whatever the arbitrary parameter t, that's going to diverge as well, isn't it? Then if I send x to the negative infinity, it's going to go to the negative infinity as well. So the bound doesn't really change. But now, if you look at this form, it becomes e to the power of negative u squared over 2. And dx will be replaced by du. Aha! That is actually the form that we already had. If you question it, well, I got the x, you got the u, does it matter? It doesn't matter because it's a dummy variable. So we know that that value will be actually square root over 2 pi. So that is great. Okay? So then, it becomes simply just what? Square root of 2 pi, thanks to the already given fact from the probability density function of a normal distribution. Then it cancels out. Square root of 2 pi cancels out 1 over root 2 pi. Hence, I'm left with just e to the power of t squared over 2, which is the moment generating function of the normal distribution. And why have we done that? Is the following. Because we want to link now the Poisson distribution to the normal distribution. Okay? Let's now try to combine that moment generating function of the Poisson to that of the normal distribution. See if I can show that moment generating function of the Poisson converges to that of the normal. Hence, I can say the Poisson will also eventually converge to the normal distribution, which is known as the central limit theorem. Let's get to it. Okay, now we found what? The moment generating function of a Poisson distribution and moment generating function of the, what is it? Normal distribution, right? And then you want to show the convergence, you see? And then we did, right? So how do we do? Let's have a look. So now you got the moment generating function of the discrete random variable, moment generating the continuous random. So now what we want to show is those moment, the moment generating function of the Poisson will converge to the normal, okay? So let's have a look. So now we got the for the z, right? Normal distribution of the expected value of 0, and then the standard deviation of 1. That's the one that's standardized, you see? So now I got the Poisson distribution. I know his PDF. We already proved it by using the binomial expansion, thanks to exponential, right? So the O minus number. So we got it. We got it, right? don't forget, it's don't be confused, it's not a multiple of x, sorry. And then the moment generating function was fancy this expected value here. However, think about this. If I send n to infinity, right? If I send n to infinity, where it indicates there are a lot of samples, it becomes infinity, right? Because if I send to infinity, it's e to the power of infinity, whatever the value that we have, it's going to diverge. We don't like that. And this doesn't directly show the convergence of the normal. And the moment generating function we have got for the normal distribution was the one for the standardized form, you see. So what I like to do is to standardize the Poisson as well. And standardized form of the Poisson converging to the normal is the aim. Let's have a look. So now what we want to do is to standardize the Poisson fusion and its respective moment generating function. So let's get to it. So we're going to standardize the Poisson distribution. So we know that the z is typically, the variable minus mean over the sigma, and that's what exactly I'm doing, because we define our Poisson distribution with what is it, the expected value of n, you see. And then in the typical, typical property of a Poisson is that the expected value is the same as the variance. Okay, that is the end. So that's why the standard deviation here is the square root of n for the Poisson. So I'm using his property, his values, to standardize it and show that standardized form of a Poisson will actually converge to the normal. So let's have a look. So now I want to find the moment generating function of that, which is going to be as such. But you can use the linearity of expected value, don't you think? So on this one, okay. This exp stands for the exponential, okay? So now, from the exponential, okay, what I've done just now is took out the, this will be e to the power of txn over square root of n, right? Times e to the power of t negative n over square root of n. Okay, so far, so very good. And for my moment generating function, the variable is t, okay? So anything other than t could actually, no, sorry. My random variable for the statistic is the x, sorry. So anything that is not in x could be considered as the independent term from the expected value. From the expected value. I'm not saying from the moment generating function, but from the expected value. So from that one can come outside of the expected value, because using the linearity of the expected value, the constant multiple can come out, where we simply have to add the constant. That's what we have. Okay, so that's what we have. And from this, what we realize, we already have the moment generating function of the Poisson. So I would simply just use it instead of what? Instead of just put the lambda here, I'm putting the the t over square root of n, because that was the moment generating function of the Poisson. Instead of a lambda, I'm putting the t over square root of n. No problem. So far, so very good. So we have that. And now what we want to do is to find the limit. But here's the thing, hear me out. So now check this out. I've got this, and we want to show how we can show the series like this. How we can show the series like this is the following. Check this out. For that one, okay, e to the power of x is 1 plus x plus x squared over 2 factorial, x cubic over 3 factorial. Don't you agree? That's the Maclaurin series of exponential, right? And for that one, okay, now I got this power here, t over square root of n. So for that, I'm substituting it, you see? So it's going to be e to the power of t over square root of n, which is going to be 1 plus t over square root of n, and then t squared over 2 factorial n, and then t cubic over n root n times 3 factorial, on and on and on. But I'm subtracting by 1, so I'm going to subtract by 1. The 1 cancels out. Not only that, I'm multiplying by n, you see? So now I'm going to multiply this by n. As you can see, therefore, it's multiplying n here. We haven't multiplied yet. But if you did, my friend, what you get is that, this power of 1, you see? So I'm going to have, negative t root n. So if you expand them out, that's going to be, plus t square root of n plus t squared over 2 plus t cubic over square root of n times 6 plus on and on and on. Okay, so that's brilliant, because you know why? That is the same thing with the opposite sign. So if you add, it cancels out, you see? And t squared over 2 is in fact independent term of the n, but the rest of the term here will have the n in the denominator, where you know if you send n to infinity, okay, that will converge to 0 because you have some value divided by the infinity. Now I got the t squared over 2. That's great. So if you send infinity, all this will vanish to 0. So now you see that the generating function, moment generating function of the Poisson, that after having been standardized will actually converge to the e to the power of t squared over 2, which you know it is the moment generating function of the normal distribution after being standardized. So hence we can show that the standardized of the Poisson will converge to that of the normal distribution, so which summarizes the central limit theorem from the Poisson. So now look, I've shown the convergence from the binomial to Poisson, Poisson to normal. So you can show therefore the binomial to the normal. So all the distribution you learn really converges to, what is it, the normal distribution. Brilliant, brilliant observation. Thanks to, again, the E. E is the essence here. Okay. Then I would like to talk about even more interesting stuff with the E, because, you know, for the AA students in the topic 1, the very first thing, the new syllabus is the proof, right? The deductive proof and inductive proof. And deductive proof, the very common question they ask is to prove the irrationality, right? The square root of 2 is a rational number. Log 2 is an irrational number. But what you often don't see is to prove the irrationality of pi or e, because they're quite difficult, you see. And now I'd like to talk about why e is a rational number using something called the auxiliary function, auxiliary equation. But it's really the same as the generated function that you just have seen, okay? So let's talk about it. But before I talk about it, I'll tell you the reason I'm talking about it, because if you look at the paper 3 from May 2021 from the AA syllabus, you have seen this very nice, interesting function. In fact, that function is so popular with the number theory, okay? And that function is often not one with the n factorial in the bottom is the one that's used, but that one is used often for proving a rational number for pi or e, and that's exactly what I'm going to do. But the reason I'm showing you this is, again, to talk about this interesting stuff within the scope of the IB. You already have seen them in the exam. There's a reason they ask you this, because it's very, very popular. So let's talk about it. So yes, for proving the rational number, what we talk about is something called the auxiliary function. Yes, for statistic, what you have seen is the following. For statistic, you talked about the generating function. It is a function that generates the aim that I want to talk about. If I want to talk about the expected value of a random distribution, then you use this generative functions to create the value that I want. Especially after having generated, if I quickly use a mathematical tool such as a differentiation, it gets to either the mean or variance. Same thing for the auxiliary function. It's got a reason. Auxiliary is an adjective of to support, you see. It supports, it helps me to find a result that I want. You see, it's a man-made up function for precisely to get some result that I want to have in particular, you see. So there's no like ultimate function to generate to prove irrationality of every number. It really depends on the number that you want to prove of. It depends on this type of the function. So there's no such So yes, it makes the things and the complex problem into the simpler form, right? But there's no like ultimate function. It really depends on the number that you want to explore, and depends on the context. There's no one-size-fits-all auxiliary function. It really depends, you see. And for proving the rationality of the E, you will use something that is similar to what you have seen in the paper 3, 2021. Let's have a look. If we look at the auxiliary function with the irrational number, so this is the function that we will use, right? It's actually, as you can see, it's exactly the same other than the divided by the n factorial. So here, then, for this one, now the domain is going to be between 0 and 1. If you restrict, then as you can see, 1 over n factorial will be the upper bound, because look, I have a product of numbers that are between 0 and 1. So x is between 0 and 1. 1 minus x is also between 0 and 1. If you power it, it gets smaller to 0. It gets closer to 0. And if you product of it, if it's less than 1, obviously it's going to stay less than 1. So what I'm saying is it's clearly less than 1 over n factorial because of the product of the numbers that are between 0 and 1. No problem. We got the upper bound, and this is a very important upper bound that we're going to use for the limit of the irrationality of the E. Okay, so let's mark that down, right? And then an important property of this function is when you start differentiating it, right? So for that, we can, if we expand them out, obviously there will be some coefficient, right? Because it was, I believe, 1 minus x to the power of n times x to the power of n, you can expand it by the binomial expansion. So the degree goes from the 0 to n. You are multiplying on top of the each term by the xn. So everything will be raised by n. So it goes from n to 2n. You see, it goes from n to 2n. So that's what we have, right? That's the polynomial term we have, and then that coefficient will be described by the binomial coefficient using the binomial expansion here. No problem, easy peasy, lemon squeezy. But then, this Cn is obviously the integer because there's the binomial coefficient with the natural number, no problem. And then as you can see, any degree that is less than n or bigger than 2n, if you differentiate, it's gonna be 0 because I don't have it. You see, it's 0. If you differentiate 0, you get 0 because this term will be described as a Cn x to the power of n going all the way to C2n x to the power of 2n. So anything before, if you evaluate 0 or differentiate 0, it's gonna be 0. No problem. This is what the result here says. Easy peasy, lemon squeezy. Alright, so now what we want to do is to talk about more property here for his nth derivative. And I will leave this one as an exercise for you to see. Okay, I want you to try yourself if you can show this identity for the coefficient. I will skip through because it's quite long, isn't it, for the video? So I like to show you the result first. Yeah, I can talk about details of this function, but for the time's sake, let me keep it short. And then for that, therefore, here that's the coefficient, and goes on and on and on. No problem. So those are the properties that you can of course discuss in your IA if you wanted to talk about the irrationality of exponential function using this auxiliary function. But I will give you for free. Those are the properties. You don't have to prove it. Okay, let's assume you got it for free. No problem. Let's continue. So I want to prove that it is irrational. So this is the polynomial we just talked about, right? And here, yes, the property here is all its derivative are integers at x equal to 0. Okay, you can prove it. And the fx remains the same if we interchange the x and 1 minus x. The function itself and its derivative are also integers at x equal to 1. X equal to 1. Okay? Sure, no problem. It's okay. All this property, I don't really need it for the result that I'm about to show you for proving the irrational number. Because we are not going to use that function directly. We're going to use one variation of it. Right? So now, what I want you to do is check this out. I got e to the power of r. What I'm going to do here is I'm going to let e to the power of r as a rational number. I'm going to show suppose. And as you can see, clearly exponential is the base e will get you a rational number. So we are trying to use proof by contradiction. So I'm going to suppose it's a rational number. Okay? I'm assuming it's a rational number. So whatever the power that it gets for the r being an integer will give you the rational number. That's our premise, right? So I assume e to the power of r is a rational number. Okay, therefore it is sufficient to prove it is a rational number for every positive integer p. We now assume that is a rational number, and then using the auxiliary function that we saw, I'm going to come up with another function. I'm going to define another function. Let me define the function like this. Okay? And of course, don't worry about it. If you ask me how did you come up with it, it's a long story. It's a long story. For me, I just wanted to conclude this video by showing you a nice property, nice proof of the exponential using this auxiliary function that we might have seen actually in 2021. Forget about it. Forget about it. That's the function we have. You don't have to know too much. Don't worry about it. Okay. So it's not difficult to show that it's integer because we saw all the derivative of the function that we defined. The lowercase fx, his derivative of 0 were all integers, right? So, and then previously when we saw the capital letter function, it was a product of the integers. You see, it was all product of this is gonna be integer, this is gonna be integer if you put x equal to 0, and I'm multiplying with all the integers also because p is just an integer number, positive integer, to the power is gonna be integer. So it's a bunch of product of integers with their sum and difference, which will result in an integer. No problem. We saw also the derivative at 1 will also be the integer because the nth derivative of 0 was also an integer. Vice versa because it was x to the power of n 1 minus x to the power of n. Okay? No problem. You can do it. Don't worry about the details. Just realize that the function that we define is going to give you an integer no matter what you put 0 or 1. No problem. Okay? So now what I'm going to do is on top of that, I'm going to multiply e to the power of px. If you ask me why, don't worry about it. Don't worry about it. Of course, for the IA, you have to mention why you're multiplying it, how you came up with it. It's going to be a very difficult discussion actually as a high school student. So I do not recommend it. But right now, let's just differentiate. And as you can see, I'm just using, product rule, right? So I use the product rule, simplify for you. This is what I've got. I use the product form, simplify for you. This is what I've got. And now what we're going to do is now to integrate this with respect to x. And as you can see by the fundamental theorem of calculus, the function becomes itself, right? And then we're going to put the 0 and 1 on top of it, right? Sorry, I think I meant to put the dx here, right? And you know, I'm integrating that, you see? I'm integrating that, but that one, by the fundamental theorem of calculus, it's going to become itself, you see? And it goes from 0 to 1. Oh, sure, sorry. If you ask me why do I have b, I just multiply the b for you. Don't worry about it. I mean, I could have canceled it out. Doesn't matter. But if you ask me why I multiply by b, it's a long discussion. Don't worry about it. Don't worry about it. But if I assume I did multiply by the b and then integrate both sides, for that one, it's going to give me just the fundamental theorem of calculus. So I just evaluate from 0 to 1. So it's going to be, what is it? b times e to the power p f1 minus f of 0. But you know that that will be an integer, right? Because we already established f of 1 and f of 0 is an integer. And that is also an integer. So product of integer will be integer. That's not a problem. That's not a problem, okay? But now the problem is one with the integral. Let's see what we get if you integrate. So that one is the right-hand side, no problem. But I like to actually directly integrate that function. Let's see what we get. So remember, this is the function that we had, you see? This is the function we had, the auxiliary function. And here we said that the upper bound is given by the n factorial, right? And then the function that we are doing right now is, what was it? If I integrate this, check this out. Our aim here right now, look, our aim here was from 0 to 1, p to the power of 2n plus 1, e to the power px times fx dx, okay? But remember, the fx was bounded by, what is it? 0. And then, what is it? It was bounded by 1 over n factorial, right? And then I'm going to write everything as the same. So 0, 1, e to the power of 2n plus 1 times e to the power px dx is what I've got, right? That was from the inequality that we already have established between 0 and 1. Remember, my domain is from 0 to 1. Okay. On top of that, then I see only the terms that are in terms of x is on the right and is the exponential form. The rest I can put them in the outside. So for that one, it's going to be e to the power of 2n plus 1 over n factorial. I'm just integrating from 0 to 1 e to the power px dx, which is pretty straightforward if you think about, right? Because that's just the, what is it? 1 over, oh, sorry, it should be p. I don't know why I wrote in my band. It should be p. Sorry, right? That was the p. Thank you. So it's p. Okay. And now if you integrate that, it becomes a 1 over p e to the power of ex. Goes from 0 to 1. You see? Okay, then becomes 1 over p e to the power p minus 1 is what I've got. Okay? So then I'm going to put that, I'm going to multiply that onto here, right? On the coefficient. Because I now successfully have managed to integrate this one. So I'm going to erase that. Okay? Right? So far, so good. So as you can see, p cancels out. So check this out. I have, what is it? p2n over n factorial times e to the power p minus 1. That's the integral that I have on the right-hand side, the upper bound, right? Upper bound. But here's the thing. If you look at this, right, in the Maclaurin series, we said that we have a Maclaurin theorem where the partial sum and there's a remainder term, right? And then for the Maclaurin series to exist, the Lagrange error has to converge to 0. Okay? And for the e to the power of x, we associate with the Lagrange error term of the exponential function as x to the power of n over n factorial. And then we show using the ratio test on the infinite series that the sequence must go to 0. Okay? As n goes to infinity. So if you look at this, whatever the value that is, I don't care. If you look at it, I got the p squared to the power of n over n factorial, which clearly suggests by the limit that we proved before, we converge to 0. But check this out. The integral that I was supposed to evaluate as a integer number, converges to 0 by the squeeze theorem, because on the lower bound and upper bound, both converge to 0. Then contradiction arises, right? The result is supposed to be an integer, I don't have it, you see? Hence, assuming the e to the power of r being rational number is a contradiction, it has to be an irrational number. Therefore, is the end of the proof. Okay. Yeah, for the last one, if you don't get it, don't worry about it. It's just to show you two things, right? The cool things about the exponential, and then that the actual exam question is somewhat related. There was a reason they gave you the x to the power of n times 1 minus x to the power of n in the exam, because that's a very popular auxiliary function for the number theory. So conclusion, yes, we prove the limit of limit n goes to infinity, 1 plus 1 over n to the power of n, using what? Increasing and upper bounded. And remember, it was actually in exam May 2017, paper 3 calculus question, right? You had to show bounded and monotonic to show the convergence. We show that, right? Very beautiful. And then we especially use the bottom expansion. For the first principle, yes, we use that limit to show, what is it? Why the derivative of the exponential becomes the exponential itself. We proved it. Very good. And for the Euler's identity, right? We defined Maclaurin series first, talked about the Lagrange error. And for the Lagrange error, yeah, you're right. X to the power of n factorial converges to 0 is a key for proving all the convergence of all the functions that you do in syllabus. Not only the exponential, sine, cosine, whatever. And then we show eventually by using the substitution of the Maclaurin series of exponential that it became e to the power of theta is a cosine theta for the real part and sine theta for the imaginary part. That's what we did. And the central limit theorem, right? We show the convergence of the binomial expansion to the Poisson distribution. And I talked about the moment generating function of a discrete random variable and continuous random variable, and hence linked with the moment generating function of the Poisson and then the moment generating function of the normal distribution, showing the standardized form of the Poisson distribution converging to the normal distribution. And all that really required your understanding with the exponential, you see? Everything here really links with E, okay? So that's why it is a very, very important thing. And yes, for the last one, we work with the irrational number, but proof of that, you don't have to know, but I just wanted to, sort of give it out to show you why it's cool, right? E is very cool. Okay, but yeah, that I just want to talk about the importance of E and to encourage you why it is important. Hence, you must know it very well. And again, there are so many potential IA topics to link with such functions. So please give it a try for you to also digest and try to find a meaningful topic potential IA. Okay, that's pretty much it for me today. I'll see you next.